Yo, so recently I decided to apply to this Dots game company, and during your first interview, they give you a coding assignment to take home and complete before your second interview. And that coding assignment is basically to recreate their original classic Dots game in Unity, in the Unity game engine. And the way it works is simple. Basically, you have multiple dots on the screen, you use your finger to connect them, and they'll disappear, and new dots will fall in from the top. However, there's another mechanic where you can see here, if you make 4 dots into a square, all of the other yellow dots on the screen will also disappear. So pretty simple, and you do this in Unity. Now, previously I had developed a Game Boy Color game. I made Fix-It Felix Jr. for the Game Boy Color. Now, Fix-It Felix Jr. was from the movie Wreck-It Ralph. This was never an actual game in the 1980s, but it was based on Donkey Kong from Nintendo in the 1980s. And so this is a new cabinet, but it was made to look retro. And since Donkey Kong did exist on the Game Boy Color, I figured I'd make Fix-It Felix Jr. for the Game Boy Color. So here we can see some of my previous work on that. And here's our title screen, and then, Felix can jump around, repair windows, while dodging the bricks that Ralph throws at him. So this was my first ever Game Boy Color game, and since I knew how to do Game Boy Color games, I thought it would be a fun additional challenge for myself to also try to create the Dots Classic game for Game Boy Color. So I have it running here in an emulator, and you can see that. So obviously the Game Boy Color is not touchscreen, so I compromised by making it use a cursor. But just like the real game, if you do create a square of dots, the background color changes to match that square, and when you let go, all of the same colored dots will disappear. And you have, basically like the real game, 60 seconds with a timer counting down to score, and you get a point for every dot that you clear. See if we can get any more squares lined up here. Now I'm using the VGB Game Boy Color emulator. It sounds a little weird. It sounds a little bit better in the Visual Boy Advance emulator, but that's okay because there's a reason why I'm using VGB, which we'll see later. Perfect, let's see if we can get this purple square here. Get a lot of these red ones here. Alright, so we got 97 dots cleared in 60 seconds, so that's almost like 1.5 dots thereabouts per second, which is pretty cool. And then, obviously we can see what this would look like at the original Game Boy resolution. And so forth. So I thought I'd make a little video about how I created this ROM, and I guess let's talk about that. So first, I found this library called GBDK, or Game Boy Developers Kit, and it allows you to write C code and compile to Game Boy ROMs. It also recommends 2 tools for creating the graphics for Game Boy. But before we talk more about that, we first have to understand how graphics work on a Game Boy/Game Boy Color. And to do that, I have 2 things. I have a Photoshop file here of basically the way the Game Boy system works. It has 3 layers, you can think of them as. The first layer is the background layer, and it consists of a grid of tiles. So if I turn on these rulers, you can see that every 8 by 8 pixels is a tile. And so the Game Boy makes the background of your screen just out of these tiles. You make the tiles separately, but then the background is populated out of these tiles. So for example, this tile is the same as that tile, this tile here is the same as that tile. This line tile is used over and over again to create the side of the pyramid. There's like these looping tiles for the ground and so forth. And you have a limited number of tiles. In fact, you can't even have a unique tile for every square on the screen. You have to reuse tiles with the Game Boy. Now this is based on Super Mario Land, so every tile has only 4 colors. You can see here's the white, light gray, dark gray, and black. Then there's the sprite layer. And the way that sprites work is that sprites are also made out of tiles, but instead of being a grid of tiles, you can move sprites individually. Now Mario is made out of 4 different tiles, which means Mario actually requires 4 sprites. There's one for like the top left side of his head, the top right side of his head, the left side of his body, and the right side of his body. And the sprite layer can move around, and the sprites can be positioned anywhere on screen, but they'll always be in front of the background layer. So they'll always overlap the background layer. And then finally, there is what they call window layer, which is usually used for displaying text on the screen or foreground objects. Some games will use it for foreground objects, so if Mario walks behind that object, he'll disappear behind it. But usually it's used for displaying messages on the screen, text, in-game menus, basically windows. But some games do use it for foreground objects, and you'll see that the sprites will actually go behind this layer. Now, the 2 layers, or the 3 layers, each behave in a unique way. The background layer is actually bigger than the screen itself. The screen is 20 tiles wide and 18 tiles tall, and because every tile is 8 by 8 pixels, the resolution of a Game Boy or Game Boy Color is 160 by 144. The background layer is just a grid of tiles. The sprite layer is just tiles that can be placed anywhere you want. They're not in a grid, they're just free floating tiles that will always be drawn on the background layer. And then the window layer is another grid of tiles, but they'll always be drawn on the foreground. And so that's basically how the graphics work for a Game Boy, and we can actually see that in action. So here I've loaded up that ROM into the BGB emulator, and you can see here's the 20 tiles wide, the 18 tiles tall, but the background actually goes beyond the screen. And that way, you can load in bigger backgrounds than can physically display on the screen, and then the screen can scroll. We can also look, here's all of the tiles that this game currently uses, and the green ones are ones that are currently on screen. So the gray ones are loaded into memory, but they're not being used. So these are all of the tiles that Nintendo has decided to load for this game. And then you can see the objects, like for example, I said Mario is made out of 4 tiles, well you can see those here. Here's the top left of his head, the top right, the left of his body, and the right of his body. And then of course they have details like, the X location, the Y location, the tile number, and various other things. And so basically that's how the graphics work. So in order to make a Game Boy game, you have to make these tiles so that you can use it within this system. These are actually kind of built into the hardware. So unlike more generic graphics programming, you don't paint the pixels yourself. You don't actually just draw to these layers with bitwise drawing routines and stuff like that like you would on other hardware. In this case, everything is made out of tiles. Your character is made out of tiles, the background is made out of tiles, and the foreground are made out of these tiles. So you have to have a way to generate these tiles. Well, I have here a program that the GBDK website recommends called the Game Boy Tile Designer. And it allows you to make up to, I think, 128 tiles, but you can change that. You can also have more tiles, but basically you can edit those. And here we have a bunch of tiles that seem to be random lines that I made. And then we have some letters you can see like press and then STA, so you can spell press start. You can see here's some arrow tiles. I only have one for left and down, but of course in the actual game, there's one for up. You can also go right. And so I accomplished that by, in the game, flipping these tiles. And of course here's the cursor, and just like Mario, the cursor requires 4 different sprite tiles to make the entire cursor picture. And then I have various other tiles here as well. I ended up using about 60 of them. 60 because it starts counting at 0, I believe. 0 is just the empty tile on top. Now, the Game Boy Color works a little bit different than the actual Game Boy, because the Game Boy had only 4 colors. Like I mentioned, it has white, light gray, dark gray, and black, but the Game Boy Color can have colors. So the way that works is you go to your palettes, and you have 8 different sets of 4 possible colors. And in the Game Boy, you can tell it which tile should use which 4 colors. So this is an interesting limitation you have to work within. It means that every tile can only have 4 colors. You cannot make a tile that has 5 colors in it. So that's a design limitation you have to keep in mind. Your tiles simply cannot have more colors. So for every 8 by 8 pixels on the screen, those 8 pixels are limited to just 4 colors. Now the next tile over can have a different 4 colors, and the next tile after that can have even more different 4 colors. But within any tile, there's always 4 colors at a time. And you end up having a lot of your palettes use white as your base color because that will be the background color that all tiles will probably want to have in common. So these are the tiles I used for the palettes. And you also get a total of 8 palettes maximum. So you can have 8 palettes for your background and 8 palettes for your sprites, and that's it. So if you need more colors than that, well, the Game Boy simply can't do that. Now, there are some tricks that you can use to kind of increase the number of colors, but those tricks are limited and they have, certain disadvantages to using them. For example, you could ask the Nintendo hardware, okay, once you get halfway down the screen, tell me, and then I'll change what palettes I use, and then the bottom half of the screen could technically have different colors. But that's kind of messy, it's involved, it's not perfect, so most games do not actually take advantage of that. So most games, you only have 8 palettes for the entire screen, and then each one of those tiles can only have 4 colors. Now, once you've made all your tiles, like up here I have these kind of weird line ones, well, you'll understand what those are shortly. The next thing you do is you use the Game Boy Map Builder. And as you can see, those random black lines actually make up the tiles for the DOTS logo for the title screen. And so basically what you would do is you would take this tile, place it somewhere, place that there, and you would start to build out one tile at a time your screen. Now there's a problem here. As you notice, I don't actually have the piece that goes down here on the bottom. But what you can do is take this piece again and tell it to flip vertically. You can take this piece again, tell it to flip vertically, and then finally this piece and tell it to flip vertically. And then now you've reused these top tiles. Now, when making a Game Boy game, you have very little resources. You have a tiny amount of RAM, a tiny amount of cartridge space, and I'll talk more about those limitations later, but you want to reuse as much as possible. Like I said, the Game Boy doesn't even have enough memory to have a unique tile for every space on the screen. You have to reuse tiles, and using tricks like flipping them means that you can save a tile that you could otherwise use elsewhere. And even though I didn't use 128 tiles, I still ran out of memory towards the end, and I had to optimize by reusing and flipping some tiles, even though I don't even use all of the available tiles anyway. And again, the palettes, like you can see here, right now it's the default palette, which is the gray colors. But if I were to switch it to like this, you can see that the pixels that were in the 4th column in the palettes are now green. I could also select it and use the palette where the 4th column is magenta, and then they become that color. So these tiles can only have 4 colors total for that entire tile, and depending on which palette you use, it determines how it looks. So I'll just take these clear tiles and erase that. So that's a little bit about how the graphics work, and you have 3 layers. One for the background, one for your sprites, one for the foreground. All of those layers reference tiles that each have a unique number. And then using these tools, you can both design the tiles you want 8 by 8 pixels at a time with limited colors per tile. And then once you have those tiles, you can use this mapping program to actually lay out more complex graphics. The reason why I made this 20 by 18, 0 indexed of course, is because that's the size of the Game Boy screen. The Game Boy is, like I said, 160 by 144. So, 20 times 8 is 160, and 18 times 8 is 144. So this is the actual resolution of the Game Boy screen. And so that's basically what I had to do to create the graphics. Now, how did I design this DOTS logo? Well, in Photoshop, I went to their website, and I just copied this graphic here. And I made a grid using rulers of 8 by 8 pixels. I then shrunk their logo down so that I could use the least number of tiles possible. So it's going to be 3 tiles tall by 11 tiles wide. I then traced over, making tiles that use, just the limited amount of colors using the palettes possible. So for example, this tile needs 2 colors for the teal, the magenta, and of course white, so 3 colors. And then because I wanted to do tile reuse, I planned ahead, so that affected how I centered this logo inside the grid, and I colored the tiles that would be unique. So for example, this tile is unique, but it can be reused down here. This tile is unique, but it can be reused by flipping down here. This tile is unique, but it can just be duplicated down here. And believe it or not, this tile can just be flipped horizontally and it becomes this tile. So this shows which parts of the logo do not need custom tiles for the Game Boy, but all of the teal ones were tiles that I would have to make. With that in mind, I went into my tile designer and one at a time, I made all of the bits for the logo, with keeping, the tile reuse in mind, and then I was able to actually create this logo. Now, from there, what you can do is export this to C code that you can use when you're developing your game. So with your tiles, you can hit export. You choose GBDK because that's what we're using. You can also use like the RGBDS framework if you're using assembly, and they have like their own object file. There's also just other Z80 assembly files and things that you can use, but we're using the GBDK C library. So you choose that, you choose where you want to export to and how many. So we used 60 tiles, I put that there, and when you hit OK, I'm not going to do it because it's already done, but when you hit OK and you look at your source code, you're given this file that has a bunch of numbers in it. And basically each of these are a byte, and every 2 bytes are 16 bits. But because you need 2 bits per pixel, each one of these is basically a row in a tile. And then every 8 or 16 of these makes up a whole tile. So that might be confusing. You don't really have to worry about that because the library actually takes care of it. The Game Boy Color knows what to do with this data. So, you just export from this program. It gives you some C code that you don't have to touch or worry about, but it gives you a name which you'll be able to use in your code later, and the Game Boy will know how to handle that. The same thing is basically true for the tile mapper. So you can select a range of tiles, and then you go to export, and again you choose GBDK. You give it a name in your code, and there's 2 things you have to export. First is the tile number, and we'll talk more about this later, but basically you just have the tile number, you hit OK, and then in this case, because we're exporting like the dots logo, it would give you a map called dots logo, where these are all of the tile indices in 11 by 3 tiles. And again, you can see in the mapper it's 3 tiles tall by 1 2 3 4 5 6 7 8 9 10 11 by 11 tiles wide. And each of these are basically which tile belongs in those spots. And so it just references the indices of the tiles. It doesn't actually save any pixel data. The pixel data was exported when we exported the tiles from the tile designer. So the pixel data comes from the tiles. And then the mapper just exports a list of which tiles to use. So I have a bunch of these exported. For example, the dots logo, the paused screen text, the press start text, the results text, the time and score text, and so forth. And where is it? Here it is. The other thing you have to do is remember that it's just a list of tile IDs. However, some of these tiles have been flipped, so you also have to somehow export the data that says whether or not a tile has been flipped. You can flip horizontal, you can flip vertical, and of course you can also change which palette that tile uses. So just like we had before, we had the D up here, and just by changing the palette, that would change the color. So get rid of that again. So you have to export that data as well. So then you go to export, and this time you add some extra fields here. The first thing you want to do is export the palette, which requires 3 bits. Then you use 2 filler bits, set to 0. and then you export the horizontal and then the vertical flip. And then this time when you hit OK, I'm not going to do it because, again, the code is already generated, but this time you would name it like, you know, ATTR or whatever, and you're going to get the dots logo ATTR file. And again, it's just a list of numbers, but this time the bits of these numbers are actually the attributes. So if you remember, we had it like this. So you have, like, you know, a byte, which is 8 bits, and the way that this format works is you have palette, 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 then 2 empties, and then you have horizontal flip, vertical flip, and then another empty. And if you have, for example, something like this, what that means is that this tile would be using palette 001, because these 3 bits make up the palette number. And it's also a vertically flipped tile because this bit is set. And so you export your attributes, and that's basically what you have to do. So these 2 tools make it extremely easy, you know, with a little bit of help from Photoshop to, you know, kind of figure out where everything belongs in a grid of 8x8 tiles. You can design your tiles, export it to C code that knows what to do. You can also design your palettes, and like I said, you only get 8 of these palettes for the entire system, but I designed my palettes. One other note of interest is because it's 8-bit, normally you think of RGB going between 0 and 255, but because it's 8-bit, your values actually go between 0 and 32, or 0 and 31 actually. It's easy enough to convert from like Photoshop. Basically, you would just open up a calculator, and let's say your color for the red value is like 170. You would just divide by 255 and then multiply by 31, and then you get, you know, 20.6, and round that up, so it'd be 21. So you know, you convert your colors by hand, but you are limited with your palette because, or with your color depth, because you only have 8 bits to work with. Yeah, so you export C code from here, then you make some maps with this program and export those into C code as well. Now, I'll briefly go over the C code, but I'm not going to spend too much time on this because obviously there's, you know, way too much to talk about. But I will go over some of the basics and kind of explain how it works. So here we have my main.c file, and I include the libraries from the Game Boy Dev Kit. Here I include the tiles that we exported, which, remember, were just a huge list of numbers, but it doesn't matter because really we just care about this variable name. And then also all the maps that I exported, so, you know, the dots logo attributes, press start, the press start attributes, etc. We include a defines file where basically I use a bunch of macro preprocessor defines. Now I use these because some of these I might not actually use in the code. Like I might not ever actually write, you know, st hand bottom left in the code, but I define them here in case I need them, and it just corresponds to its tile number. And because they're preprocessor defines, they have no impact on your ROM size. So if there's one that I defined but I didn't use, it's a little bit different than making a constant that you didn't use, and it's just ignored. It's not part of the final build. I also have some defines for the sound effects. The way that sound works on the Game Boy Color is you have these registers, which are basically bits of memory for that you write to for the processor to know what to do. And by setting these different register values, the Game Boy will play a sound every time you change these. So these sounds were actually reused from my Fix-It Felix game. Because I was going in a hurry, I didn't want to design a bunch of new sounds, and these worked well enough. So that's why they're called like jump and fall and fix and fist and everything. But they worked fine for this game. And so basically I have a define where you say SND jump, and then it sets all the registers necessary for that particular sound effect. So I have my defines file. I encapsulated all the logic for the title screen in this file and all the main game logic there. To clear the screen, I basically have a export of tiles that's 20 wide and 1 tall of just empty tiles. And there's 2 banks in your VRAM where the video memory is stored. Bank number 1, actually the second bank, is where you store your attributes. So remember, we had to export well, it's gone now, but we had to export the attributes bitwise for whether a tile is flipped and which palette it should use. So you say VRAM bank 1, and then you set the background tiles to your attribute tiles. So here I'm just setting column 0, position I, 20 wide, 1 tall, basically the clear line data. Then I set it to the VRAM bank 0, which is the first bank, and I loop again, and I set it to just the clear line, so all empty tiles basically. Here's where you initialize your tiles. So basically you say, here's your palettes that was exported from the tile builder. I said my background tiles and my sprite tiles should use the same palette, because for this game I didn't need different palettes for the sprites. It was fine just using one palette. Then you set the background data and the sprite data. Again, here's that main tiles variable. So like I promised, this is a big list of numbers, but really it's just called main tiles, and you tell the Game Boy, I want to use those tiles for the background and I want to use those tiles for the sprites as well. Then in our entry points, you have some kind of boilerplate stuff. By setting these registers, you initialize sprites as well as start the sound for the Game Boy Color that turns sound on. We call this function, again, where you load in all that data to memory. And then we have a main loop where it shows the title screen, and once you hit start, it goes to the game. And then once the game's over, the while loop goes back to the title screen. We'll briefly look at the title screen. So one thing I like to do is kind of namespace by putting the name of the file with an underscore for its methods and for its variables. Now, C does not have classes. It does have structs, but the Game Boy compiler doesn't like structs that much. It's a very limited, kind of glitchy compiler. So I'm basically just using globals here, and in fact the documentation for the compiler says that it prefers globals. Now, a lot of people would argue that globals are a bad habit, and I agree, but because of the optimization that the compiler can do with globals versus having local variables, a lot of times I'll make things global, even though they don't necessarily need to be. But these are global program-wide, so if I'm in the game code, this global would also be available. So because it's only for the title screen, I prefixed it with this, so I know that this variable should only really be used in titlescreen.c. And these methods are only going to be defined and used really in titlescreen.c. So the start, initializes some of those globals, it clears the background, it sets the dots logo to be at position 5, and we can see here that in fact this top left tile is row 5, column 5, and it copies over 11 by 3. And again, this is 11 wide by 3 tall. And it copies over both the attributes for tile flips and palette colors, and then it sets the VRAM bank to 0 and copies over the tile data themselves. Now, here's another interesting quirk. So move background, X and Y, actually allows you to scroll the background. So just like in Mario, we can see that the background is bigger than what fits on the screen. So if we unpause here, walk a little bit before I get killed, you can see that this box that represents the screen scrolled over. So now we're viewing a different amount of the background. Now, when you set it to a positive value, the screen scrolls over. So the background appears to go to the left because the screen has in fact gone to the right. Now, when I designed this logo, I designed it to use the least amount of tiles possible because, like I said, I wanted to be able to flip some of these tiles and be able to reuse some of these tiles. So focusing on these dots, I realized I could design this one tile and then flip it vertically to make this tile, flip it horizontally to make this tile, and then flip it vertically and horizontally to make this tile. But if I had the logo, I guess like this, then these tiles for the dots would not evenly divide into things that I can reuse, because now this side is a lot bigger than this side doesn't match this one. So if I were to center the logo, it would not have divided as nicely. The problem is, if we go to dots here, and unpause, the logo is not actually centered on the screen. Well, it's centered here, but if you look at this, it's not centered. There's actually slightly more pixels on this side than there are on that side. So by deliberately scrolling the screen 3 pixels, it does center that. This is a macro that comes with GBDK to turn the screen on. Now that we're ready, we turn sprites off, we hide the window layer because we're not using it, but we do want to see the background layer. We enter the title screen loop, and we're only going to be editing the tile VRAM bank, so we just set that up ahead of time. And then we have a main loop that says while joypad and bitwise operator start, and basically, and then a not. So we're basically waiting for the player to press start. And the way that this works is using bitwise operators. So when you call joypad, it gives you a byte in return. But the bits for that byte determine what buttons are being pressed. So I made this little map up here for reference. And basically the way that it works is you have up, down, left, right, BA, start, select as the bits in a byte. So remember, a byte is just, you know, either 8 ones or zeros. Move this over here to match. And so if the user is pressing down, then the column for down will have a 1. If the user is pressing B, then the column for B will have a 1. So if you have, for example, this, then when you call joypad, if the number you get back has these bits enabled, it means the user is pushing both down plus B. So to check what buttons the user is pressing, you use bitwise operators. So here we say you get the value of the joystick, which is going to be some byte with bits either on or off, and you say bitwise and then you use one of these defines to check if start is being pressed. So basically, we have a while loop that says while start is not pressed, increment the blink timer. If it's over the blink length, switch the press start to be true or false. Again, using the verbose global, but it is what it is. And then we either show the press start characters on the screen on the background layer, or we show empty tiles on the background layer. And then we basically loop until they press start. And then once they press start, we want to wait for them to release start. So there's another while loop that just says while start is pressed, do nothing. And as soon as they release start, then it'll play the sound effect for start, which remember is down here. So that's basically the same as copying and pasting these register values, and that causes the start sound effect. Of course, then title screen loop exits, then title screen start exits. We go back to our main loop, turn the display off, start the game, which, and then this file is a lot more complicated, so I'm not going to go over it, but it's more of the same. You know, I have all of my functions with like kind of the namespace underscore because they're all game functions. I have all my global variables. Because this is like the core of the game, I didn't do the namespacing like this for all the variables. I should have maybe, but I figured for this, because this is really where the logic and the heart of the game live, I didn't want to have to type that every single time. But if I had another screen, like title screen, I would have prefixed those. But you know, there's the, I have a lot of comments as well. But there's the game start, which, you know, sets the time and score on the screen, the background tiles. It does a bunch of init stuff, etc. But yeah, this is a kind of a long file, so I'm not going to go over that stuff. But that, in a nutshell, is how you develop with GBDK. It's mostly just about setting up tiles in the correct places, moving tiles to the correct place, moving your sprites to the correct place, and then everything else is just regular C code. Now, there is a couple gotchas that I want to talk about. In the compiler for the GBDK, it's a little quirky. So the Game Boy uses a modified Z80 processor, which is an 8-bit processor, and it has 4 registers for kind of temporary working opcodes. Now, this processor was never designed to run C code. Original Game Boy games would have been made purely in assembly, and the compiler has some quirks. As I mentioned earlier, it strongly prefers globals, but you can have local variables, so let's see if we have one right. So I have this comment that says, due to limitation in GBDK and LCC, local variables always need to be defined on top. Now this is a weird quirk, but basically, if you have local variables inside a function, they have to be defined on the top. You can't do anything else. the top of your function has to be for defining variables. So for example, if we got rid of this int x and instead we said like that, that would actually cause the compiler to fail, because it doesn't like the fact that you're trying to define a variable inside the actual code. The variable has to be defined up here at the top. So that's a weird quirk. Another quirk too is that if the lines have too many operations on them, or if you nest too deep, like if I were to try to put like a third nested for loop in here, it would not compile correct assembly. So there's all kinds of weird quirks that you have to kind of deal with, but basically, in a nutshell, that's how you develop for Game Boy Color using GBDK. And as you can see, I like to comment a lot. I comment almost every line, and I also use, good variable names, good method names to kind of explain everything. I also use the doxygen syntax. Let's see if we can find one here, where I pass in the param and all that stuff. So if you were to run doxygen on this, you'd be able to see a web page of all the documentation for the entire program. So I'm very, very careful to always comment my code. So this almost acts as a tutorial. If you wanted to make a Game Boy Color game, this would probably work. I also have a how to compile guideline in here. And speaking of that, let's talk about compiling. So I'm going to go to the title screen, and where is it? It's here. Okay. So the way it works is you have your source. Here's my main.c, and I'm actually going to delete my ROM. And then you have your command line. I use cgwin, or sigwin, sorry. And I like that. I also like light themes, as you can see. But you could also do this on the DOS console, or I think this works on Mac as well, so you could do it on Bash on Mac and everything. But basically, the CLS is my code. You don't need that. But basically, we'll just get rid of that, I guess. You say LCC, which is our Game Boy compiler. You put this flag if you're doing Game Boy Color. If you do not put this flag, it'll make a regular Game Boy ROM. You say your output is going to be dots.gb, that's your ROM file that you make. And then your main C file. So we hit enter, and sure enough, a ROM appears. So if we go into our emulator and drop that ROM in, it works. Now, to prove that this did actually compile something, let's change the scroll on the title screen. We're now going to recompile. And now, when we drop our ROM in, the title screen is a lot more to the left because we scrolled 30 pixels instead of just 3. So we'll put that back, compile again. I have like super reflexes for killing that Sublime text window. And now drop the ROM in, and it's back to being normal. So it's actually, that straightforward. Write your code, compile it with this command, and you'll get a ROM file that works in emulators. Now, there are some other gotchas. As I was developing this game, I was developing it in mind to actually have it be physically built. I wanted a real cartridge with this game on it. So I found this guy who would, for $10, you could choose custom ROM, and he will sell you a Game Boy cartridge with your ROM on it. And the PCB looks like this, and in this little memory chip exists your custom game. Now, there is a problem. As you can see, it's called a 32 kilobyte Game Boy flash cart. And that means you cannot make a game that is bigger than 32 kilobytes. And you can see right here, my ROM is 32 kilobytes. Now, some Game Boy games are bigger. Like, for example, I think like the Zelda games or Pokemon games are like 4 megabytes. But the problem is, when the Game Boy was originally designed, the original black and white Game Boy, it was designed to have 32 kilobyte games. And this memory chip would have 32 kilobytes of your game ROM on it. But as developers started needing more memory, they started putting more of these chips on one cartridge, so there'd be like 4 of them. But you can't access 4 of them because the Game Boy was never designed to do that. So they put a 5th chip on there called a memory bank controller. And what that allows you to do is, with the pins, the Game Boy can talk to the memory bank controller, and it can switch which of the 4 banks that you're reading and writing from. So this makes programming more complicated because you can't read data from a bank if that's not the one you're switched to. So you first have to switch to the bank that you know where the data lives, then read that data, and then switch back to another bank. And the banks can both contain visual data like graphics and sounds, or I should say asset data like graphics and sounds, but they can also contain game code. So in some cases, you can run code that exists in one bank and then switch to another bank and run code from that bank. But if you try to access code from this bank, it won't exist. So you have to first switch back to that bank and then run that code. So it makes programming more difficult, but I did have to do that for the Fix-It Felix Jr. because, as you can see, I have a lot more custom sprite work on this game, and it just required more memory. But the problem is, in order to have a custom cartridge made with that extra memory, you have to have someone who's able to do that. Now, this guy can make a Game Boy cartridge for $10, but it's at that 32 kilobyte limit. And I wanted to use this guy, Catskill Electronics, because, well, one, $10 is a good price, and two, it's more complicated to do the memory bank stuff. Now, this guy sells a cartridge for $30, which isn't terrible, and it says it uses Memory Bank Controller 5. Now, over the course of the Game Boy, they used multiple different memory bank controllers. So I think 5, there might be more than that. But that also means when you compile your code, you have to target one of these controllers. And if you target, let's say, memory bank controller number 3, and you try to put your code on this cartridge, it won't work. Also, the developer of this cartridge might have mislabeled this, or your compiler, you might have somehow messed it up so that it doesn't work. Also, this guy does not flash them for you. You have to buy your own flasher, which is another bit of hardware, which you have to buy for like $50. That takes your ROM and puts it on this cartridge. So it adds a lot more complexity, it adds a lot more cost. I have to buy the flasher, then I have to make sure that my code compiles specifically for MBC5, and if it's anything else it won't work. And the cartridge is more expensive as well. So, and you also have to buy the right size as well. So I didn't want to have to go through the headache of trying to mismatch or match the memory bank controller, or having to buy the flashing machine and then buy these cartridges, when this guy will not only put the ROM on there for you, but he'll do it for $10. The only limit, of course, is that you have to get 32 kilobytes. So one of the design decisions I had to make was to try to keep everything within 32K. And it was scary because at the end, I actually ran out of space. The game was like 90% done. I could select dots, they would disappear, new dots would fall in from the top. But the only feature I didn't have, let's see if we can somehow arrange it here, was when you make a square, the background color has to match the color of your square, and then when you let go, it has to get rid of all similarly colored dots. Here's another square. Background goes to yellow this time, and then all the yellow dots go away. And I got it to the point where the background color was working, but when I started adding the code to remove similar colored dots, I actually went past 32 kilobytes, and the compiler will error. The compiler knows you're not using banks, and it will tell you that you've made a ROM that's too big. So at this point, you either have to start using banks, and then the compiler will be okay, or you have to start removing content, or optimizing. So I literally went to my source code, went to main.c, started here, read every single line of code for the entire program, and rewrote code and tried to optimize things specifically so that I could save enough memory to finish the game and still have it in 32 kilobytes. And you can see the game is pretty simple. We have very few text letters, basically just the letters that were needed for numbers and for the text on the screen. A very minimalist title screen where it's just the logo. There's no fancy graphics in the background. And of course, when you play, there's the graphics for the hand. There's the graphics for the dots themselves. When you select one, there's the arrow graphic. When you move, it temporarily makes the dot bigger. Those were different tiles. And of course, the different arrow tiles for the different directions. And that's it. That's the whole game. I mean, there's the arrows, there's the pointer, and then there's the dots and the lines between the dots. So not a lot of graphics, and this is an example of what you can fit in 32 kilobytes. I like to think I did it pretty optimized. You don't get a lot for 32 kilobytes, so that's something to be aware of. Now to test, obviously I've been testing in this emulator, and I also purchased an EverDrive for the Game Boy Color, and the way that this works is it looks like a regular Game Boy Color cartridge, but right here there is a micro SD card slot, so you can actually take your ROM that you compile and put it on a micro SD card and then test it directly in a real Game Boy Color. So I do have a Game Boy Color on me, and I use this to debug on real hardware when I wasn't just testing in the emulator. So after I had my ROM finished, I interfaced with this guy, emailed the ROM to him, and I got some of these cartridges in the mail. Now, there is a thing to be aware of when you're developing for Game Boy Color specifically, is that the cartridge type matters a little bit. Now, this gray cartridge with the little corner out of it was meant for the original Game Boy. And when you put the cartridge in the Game Boy and you turn it on, a little tab will go here and prevent the cartridge from being pulled out while the Game Boy is on. This doesn't really hurt the cartridge or the Game Boy that much, but I guess Nintendo felt the need to do that. But if you recall from back in the day, there was two types of Game Boy Color cartridges. Now this Game Boy Color cartridge has that old style cartridge with the little notch out of it. So this game, Wario Land 2, will play on a Game Boy Color, but it will also play on the original Game Boy. So this is backwards compatible. It'll just play in black and white. But a Game Boy Color game from the era have these clear shells, and this will only play on a Game Boy Color. You can see here it says only for Game Boy Color. It does not have the notch out of it. So if you were to try to put this in an original Game Boy, it would fit, but you would not be able to turn it on. So this game will not work on an original Game Boy, only Game Boy Color. So this guy sells games for Game Boy Color, but he uses this cartridge. So from this website, I found a clear green plastic shell for $1.69. So I bought a few of these, and the PCB that he gives you actually fits in both. Nintendo used the same shape for their cartridges internally. The screw is in the same place. So even though he shipped it with these cartridges, I just went here and purchased some of these and put the ROMs into this. And so that's basically how I made the physical cartridge, keeping in mind I had to keep it down to 32 kilobytes. And one other thing that I wanted to mention is, like I said, I went to the trouble of getting a clear plastic shell that would match the Game Boy Color style games. And if you think about the old school Game Boy Color games, the ones that had this shell were reverse compatible with a regular Game Boy. And I could have technically made my ROM reverse compatible, but it would have been a little bit weird. Allow me to show you. So if we go into our emulator here and reset the cartridge, what I can actually do is go into options and tell it that we want to use a regular Game Boy. And when I hit apply and then restart again, it now loads as if this was an original classic Game Boy or Game Boy Pocket. Now the first thing you'll see is that these are not flipped. And these dots look weird because these tiles also expect it to be flipped. This little piece right here should be flipped horizontally because it's a copy of the piece that's here. And like I explained, you can select a tile and have it be flipped vertically or horizontally, and you can also change its palette color. And also, like I explained, when you're doing your export, you add a few things here like the palette. You add a couple empty fillers. You add the horizontal flip and the vertical flip, and then you export this data as well. But this entire system was designed for the Game Boy Color. Because the original Game Boy didn't use different palettes, every single tile always had the same palette. It was always, white, light gray, dark gray, or black. There was no need to export palettes for the tiles. And because there was no need to export the palettes, there really was nowhere to store horizontal or vertical flipping. So the original Game Boy does not support tile flipping, believe it or not. So it's literally just reusing the same tile because this hardware does not support tile flips. That was introduced with the Game Boy Color because they now had memory free, since they had to store the map. They might as well use those other bits to store other properties like flipping the tiles. But if we hit start, all of the dots will be the same color. So it's a little bit tricky to try to figure out, where you can make your selections because they all look the same color. Now, I could have worked around this. For example, I could have made, obviously the background is white, but I could have made some of these dots light gray, some of these dots dark gray, some of these dots black. But there's, I think, 5 total dots. So I would have had to do some weird things, like maybe make some of the dots striped, some of the dots maybe would have like a circle in the middle of them, or maybe they'd have like an X through them or something. So I could have made the game work in black and white mode, but I couldn't do that because I was already running out of memory. And like I showed you, it doesn't support tile flipping. So I would have had to actually made the reverse tiles just to get it to draw correctly, because I couldn't reuse tiles and flip them. But then I'd also have to introduce new tiles for, having stripes or a checker pattern or having a cross through them, just so that the game could be playable, because obviously if all the dots are the same color, that doesn't really work. The game is basically designed to be a Game Boy Color game. If you look at their actual game, it's color-based. So while I could have made this backwards compatible with the original Game Boy, it would have taken more space, which I really couldn't afford, and also it would have been kind of dumb, since the game really, works better with color. So this is what my game looks like if you force it to run on a Game Boy original. But if we put it back on Game Boy Color and then load it, you can see the flipping does work, and of course we have all of the colors. So when talking about, the difference between cartridges, if I had used his cartridge with the notch out of it, that would have allowed somebody with the cartridge to put it in an original Game Boy system, and they would have had that experience where all of the dots look the same. The title screen is kind of glitched because you can't repeat tiles. There's various other graphical glitches as well. So when I decide to switch to the Game Boy Color style case, it doesn't have that notch out of it, so it won't fit into an original Game Boy. So that's why I bought these. So I could have designed it to be backwards compatible, but it just would have taken more memory, and it wouldn't have been as fun. It would have been kind of dumb. So I thought I'd mention that because the emulator does allow you to, force which console you want to use, and clearly it doesn't make sense to be backwards compatible. So, I thought I'd kind of just show you that and why I chose to go with the custom Game Boy Color cartridges, or the cases, because it just doesn't make sense to include backwards compatibility. I guess a couple other quirks, I'll just show you an example in the emulator. So this emulator is really cool because you can actually see what's happening in RAM while you go, just like we saw for Mario, the tiles that were used and the positions that they were used at and so forth, and where the screen is. For dots, I have the same thing. So let me just reload the cartridge here. So when it first starts, it copies the dots logo to these positions, and it has the blinking press start. And in code, what's happening is the title screen. So we have this loop that basically says while start is not pressed, increment this blink timer and either show or hide the press start. We show it by copying the press start tiles, and we hide it by clearing those tiles. So we can see that that's in fact what's happening here. Your background has the press start tiles, and then they're cleared, and then they come back. Once we press start, it draws the grid, and obviously you don't see the pointer because that is a sprite. That is not part of your BG map. Of course, you can see the pointers here, and those are sprites. I also have the arrows, but they have a slash through them because they're not currently visible. But if I were to go here, you can see the pointer disappears, so it has slashes through it now. But the arrows for the left, well, I guess only the left one is available. we go over, and now only the right one is on screen. So it's kind of cool. This program shows you what's being used at any time. These are all the tiles I loaded. As you can see, compared to Nintendo's Super Mario Land, I have a lot fewer tiles, and that's probably because Nintendo was using a bigger cartridge size, and also they were dealing with black and white, which takes up less memory, so they have more space to work with. But outside of this, these are all the tiles that I used for the entire game, so only the colors. And you just saw right there, it scrolled down, and I actually, let's restart this again. We'll get, I guess we'll get a couple points here. All right. You can see I'm changing like the tile for the time in the background, and these are all the tiles on the screen. If you watch here as I clear some, when I let go, you'll see that the dots actually slide in the background. I'm actually editing the background. So let's do that. So these dots are not sprites. I'm just, changing the position and color of tiles in the background, as opposed to using sprites. But even though the game has not ended yet, you'll see that there's results here with empty values next to it, score, your best score, and the press start text. All of that's loaded in memory, but it's just not visible because it's below where the screen is. And so once our time runs out, you'll see it scrolls the screen, and that becomes on display. Also keep in mind this time and score up here. That'll be important. So as it starts scrolling, the time and score disappear, because you can see the screen actually wraps around to the top, and if I had left the time and score up there, it would have shown here at the bottom, which would have looked weird. So the dots are all still visible, they're just off screen because we scrolled down. But what's interesting is now that the game is over, even though I hit enter, whoops, let me fast forward here. We're back at the title screen, but that stuff is still on the screen. I never bothered to clear it because that would take up more code and more ROM size, so who cares? So even though you're on the title screen, it still shows off screen your previous results, which is kind of funny. And then when you hit start, that stuff is still there. So we'll try to get a higher score this time. And you can see, it still shows your previous score is 0, your previous best is 9. None of that has changed yet. Sometimes my keyboard's weird. There we go. Alright, so we have a much higher score now. So we'll just wait for that time to run out, and what you'll see is as soon as the screen starts scrolling, it will update these. And when it's about halfway down is when the time and score will disappear. Alright, here we go. So you can see as soon as it scrolled down, it updated those and cleared the time and score. And once we... I keep hitting it too fast. Let me fast forward. There we go. It still shows, your previous thing at the bottom. And of course, if you reset the ROM, it doesn't have it yet because we haven't gotten to that part of the code. But as soon as we press start, it's there, and it will remain there basically indefinitely because it's just off screen. So I thought that would be cool to show you kind of how like the RAM and stuff is working for the ROM. This emulator is BGB. It's pretty good for helping you debug and stuff. It also has other debug features like there's a debugger where you can actually see the assembly that's been generated. You can see where you are and kind of what's happening, which is pretty cool if you know assembly or if you want to like play with the assembly. So that's a pretty cool emulator to help you debug and stuff. So anyways, that is in a nutshell how the C works. Like I said, I'll provide this. It's all commented extremely well. That's how the tools work for designing your tiles, exporting the C code for them, designing your maps and exporting the C code for those. You saw the command line for building the ROM, and then the ROM does in fact compile, which will work on a Game Boy with an EverDrive. And if you can manage to keep it under 32, you can buy one of these cartridges for $10, which is what I did and is pretty awesome. If you do need more space, you can buy one of these cartridges. You have to buy a flasher, and you have to make sure that you compile for Memory Bank Controller 5. That's all complicated stuff that I won't get into, but that's also an option. So after I had the cartridges made, the last thing to talk about is making the package. So I basically Googled a template that looked like this, and I think this was another fan-made template. Obviously you can see where they pasted their graphics and then just have blue for the flaps and the folds and stuff. And it seems like this guy who made this template scanned one of the box arts and kind of painted it out and then pasted his graphics on there. This could be a real game, I don't know what it is, but for whatever reason, this is kind of an awkward looking template. But I printed this out and it wasn't perfectly to spec. When I folded the paper together, it was kind of awkward dimensions. It didn't quite work right. So what I did is I Googled the dimensions of Game Boy Color boxes. I found this graphic, and it's for Game Boy Advance, but Game Boy Advance used the same box shape as Game Boy and Game Boy Color. And so it looks like the front and back are 5 by 5 inches, whereas the sides are 15 by 16, or 15/16ths of an inch. So in Photoshop, using 300 dots per inch, I made these things. So here we have a square that when we select it and we go over to inches, it's basically 5 by 5. And if I had selected it a bit better, it would say exactly 5 by 5 there. Like the widths are, well, it's not going to show 16ths, but you get the idea. So I basically made the correct tabs all by hand so that everything would fit perfectly, so it's a little bit less crooked than this template I found online. And I simply put the Dots logo and stuff in there. I got some of this from scans I found online, and basically customized it. This copy is actually from the official Dots website, so I didn't have to write anything. I took some screenshots from the emulator and put some text under them. So I basically made a box, and I found a place nearby that allows me to print on glossy cardstock. You have to print on 11 by 17 because the total size of this in inches is 12.3 by 7.8. So obviously that won't fit on a regular printer. A regular printer does 8.5 by 11. But we need 12 on one dimension, so I had to use bigger paper size. So I found a printer nearby who would do that for me. So he printed out some awesome boxes for me, and then I was able to cut along the edges, score and fold. I actually didn't leave these lines in there. I instead used this, where it was just slightly gray so I could figure out where to cut with the razor blade, but I didn't want to have lines there. I wanted the package to be seamless. I also found a cartridge label. This template I found online. The way that it works is 3 letters are the Game Boy machine code, so CGB was Nintendo's code for Color Game Boy. We tend to think of Game Boy Color, you'd think it would be GBC, but Nintendo calls it CGB. Then you have 4 letters that are the game code. Now usually these are random letters, but I just went with dots because that's the name of the game. And then of course your region. And then on this side it says this side out as a reminder of which way to insert the cartridge. So I also had these printed. The same guy could print them on sticker paper as well. So I had a bunch of these printed on sticker paper. To make them have a laminated surface, because the sticker paper was matte, I just took some clear package tape and stuck it over the sticker and, pressed out all the bubbles and made sure it was really smooth. But that gave it a nice glossy finish and made it very waterproof and durable, and it looks exactly like a real Game Boy Color game. So I printed out those, stuck them on the cartridge, and then I had physical cartridges for my game. And I think, that about wraps it up. That's all the work that went into making a custom Game Boy Color game. I hope you found that interesting. I hope you got a little bit of insight into how these old consoles work. It was definitely a fun project. And yeah, so we're about at an hour, so I think we'll leave it there. I hope you enjoyed.